This presentation is brought to you by the SDG Decision Education Center.
Hello, and welcome to the Pitfalls of Heat Maps, Powerful Alternative Risk Management Methods, brought to you by SDG Decision Education Center and Texas Executive Education at the University of Texas. I'm Lynn Slattery, Director at Texas Executive Education and manager of a portfolio of open enrollment programs designed for busy professionals. This portfolio includes the Strategic Decision and Risk Management Certificate Program, which brings together the academic research and practical application teaching of UT faculty and 35 years of experience in strategy consulting and decision education of SDG, and serves as the basis for this webinar series. We are proud to be partnering with SDG on this series of programs. If you've missed our previous webinars on decision quality, negotiation, game theory, biases, and risk, please check out the recorded version on the SDG website, shown in the gray box of this slide. And while you're there, you may also want to register for our upcoming webinars. The 7 Deadly Sins of Strategy will be a two-part series. The first will air on October 18th and the second on November 8th. Today, I'm excited to have an expert in the field of decision quality, Dr. Eric Bickel, here to share his knowledge with us. Eric is an associate professor at the University of Texas at Austin and the academic director of our SDRM program. Dr. Bickel has also taught and consulted for many years with SDG. Eric, I'll turn the floor over to you to begin.
Thank you, Lynn. Pleasure to be here, and good morning or good afternoon to everybody. Today I want to talk about heat maps and their use in risk management and decision making. And there's 3 goals for the presentation today. The first is to make you aware of the broad use of heat maps for managing risk and informing decision making. The second is to illustrate and discuss the potential dangers of using this tool. And the third would be to encourage you to use decision making methods and risk management methods that are based on sound research and theory. And just have a little picture of a risk heat map here to the right, and we'll go over that in more detail. This presentation is based on some work that I did with Professor Radar Bratvold at the University of Stavanger, and then his student Philip Thomas. And we published this in a Society of Petroleum Engineers journal in 2014. And so if you're interested in that paper, you could follow up with me for more detail. So first, we wanted to start with a poll question, and that is, to what extent are heat maps used within your organization? I want to get a sense from the audience here. First choice would be you haven't seen them before, these are new to you. Second, you've seen them and they're used occasionally. Third, they're used for many decisions. And fourth, they're used for almost all the decisions we face. So if you'd make a selection there, and then we'll feedback the answers and get a sense for how familiar the audience is with heat maps. Okay, so the poll's closed, and it seems that for most of you, 50% that heat maps or risk maps are used occasionally, 31% used for many decisions. Really, minority either hasn't seen them before or they're used all the time. So about 80% usage that they're used a lot or at all. Okay, so in terms of an agenda, I wanted to talk about what heat maps are, how they're being used, and then talk about the underlying theory for heat maps, and then discuss some of the flaws that are built into them, and then briefly mention how you could learn more. So a heat map is a graphical representation of the likelihood or probability and the consequence or severity of some event. And so on this scale, I've shown the probability of some particular event. It could be highly unlikely, unlikely, possible, likely, or very likely. And then on this dimension, we have the severity. Potentially there's no impact, a minor impact, all the way up to extensive impact. And so this 2x2 grid is set up, and then the corresponding squares or rectangles here are colored in some way. Usually red at the top for these are critical things we need to worry about, green here on the other end that maybe these are things we don't need to focus on, and then yellow for things that are in between. Okay, the use of heat maps, as we saw, I think, in the poll and then in some of our research, is they're really considered a best practice across a number of domains. They're used in many SPE publications. That's the Society of Petroleum Engineers, so heavy use in the oil and gas industry. They're widely advocated by risk managers. There's training courses, consulting firms, and so on. You can just Google heat maps and you'll be overwhelmed with the number of results. They're also included in certain risk standards. The American Petroleum Institute, they say that presenting the results in a risk matrix or heat map is an effective way of showing the distribution of risks for different components in a process unit without numerical values. So it's kind of an operational risk assessment. ISO, the International Organization for Standardization, they say that the risk map is a strongly applicable tool for risk identification, risk analysis, and risk evaluation. And really, a lot of people, I think, view the creation of heat maps as synonymous with risk management. I mean, that is how risk management is implemented in many circumstances. They're easy to create. So you'd start with, we could think about all the risks that we might face, create a risk register. We could also think about upside, but I'm going to set that aside for now. We'd create this two-dimensional grid, divided up into categories. Often each category is given a score of 1, 2, 3, etc. And then we place each risk within this grid based on an assessment of its likelihood and consequence. And then we'd prioritize and manage the risks in a comprehensive and a visible way. Okay, pretty straightforward. It's intuitive, easy to follow, and produces these charts, which I think people find appealing. As I mentioned, these tend to be focused on downside, though not exclusively. But it tends to be things where we have some probability of a loss. Risks are then managed by their color. So red risks are worse than yellow risks. And this is an example we took from an SPE publication. We've got here we have the consequence on this axis. Incidental, which was defined as being less than $100,000, minor between $100,000 and $250,000, severe 5 million to 20 million, and then catastrophic was anything above 20 million. And then on the likelihood scale, rare was defined as being less than 1%, remote 1 to 5, unlikely 5 to 10, seldom 10 to 20, very likely above 40. Right, so one thing to notice is the buckets don't have the same size. This is 150K, and this is a spread of 15 million. And the same could be said on the probability scale. And then here, the authors used a consequence rating from 1 to 6. So 6 being the worst in terms of severity and probability. Okay, and then the red risks, those are critical. We need to deal with those in some way. Yellow risks, that's medium severity, address those once we've addressed the red risks. And green risks might require no action. And this was an oil and gas example, a drilling example, and so there was some possibility to have severe losses of drilling fluid, and that was identified as being a risk that we need to pay more attention to. The chance of a blowout, because it had lower probability, was a yellow risk. The risks are often scored and then ranked. Started to allude to that by multiplying the likelihood and consequence scores. So for the example below, we had severe losses. The consequence was 1 to 5 million. Probability was 40%. Well control, 5 to 20 million dollar loss, 10% probability. Blowout, greater than 20 million with a 5% probability. Those are then placed here in the risk matrix. So we had severe losses, 40% probability would be here, and the loss, if it occurs, 1 to 5 million. That's where we put it. And so that has a score of 4 on the consequence and a score of 5 on the probability. And those are often multiplied to yield 20 to come up with a risk score. And we could do the same thing for well control. 5 times 3 would be 15, and then for a blowout, 6 times 2 would be 12. And then we could rank these risks from most significance, what we should focus on, potentially to the least. Okay. So the heat maps are purported to offer many benefits. They're easy to create, easy to assess. We're using verbal statements of impact and probability. Easy to score. It's often argued that they improve communication. And really, one of the primary benefits that's often stressed is that anyone can use them and interpret them. So it sort of democratizes decision-making and risk management. So that's an introduction. The next section here is, well, what's the theory underlying these heat maps? And does it matter how you create them? Do the buckets have to be the same size? Can they be different sizes? Does it matter when you multiply these numbers together? And the theory is easy to put on one slide, and I have all of the theory within this box. There is no real, I would say, academic grounding and empirical testing of heat maps, certainly regarding their construction and, does their design make a difference? Could you alter the decision simply by how you choose to design the heat map? That would be concerning, or there would need to be guidelines to make sure that everyone knows how to design them so that you don't do that. And really, they've grown up in isolation from the science and practice of decision making under uncertainty, which is an entire field unto itself. So if these heat maps really are the gold standard of risk management, their design and development needs to be addressed. How many categories should you create for each dimension? Right? Should it be 5? Should it be 6? Should it be 3? How should you divide each dimension? Does it matter if you don't divide each dimension evenly? If you use a numeric score, this 1 to 6, should we count up, or does it matter? Could we count down? Could we go 6 to 1 and then prioritize by the smallest number? How do you color it? Can you make any score you want yellow, for example? And is there any problem with multiplying these scores together? And a number of researchers and consultants have looked at these various questions. We summarize them in our paper. Don't have time to go through all of them now, but just hit some highlights. But in terms of what we've seen, there really are no recommendations or best practices for how to address these things. And if you think about it, there really is no logical argument to be made if you want to create buckets in terms of how big that bucket should be and if those buckets should be the same size, for example. So what are some of the flaws that are built into heat maps? There's 3 that we that are new that we address in the paper. The first is what we call the risk acceptance inconsistency. But basically, and I'm not going to go through this in detail given the time, but you can read about it in the paper. But essentially, you can set up risk matrices or heat maps such that you accept risks that are worse than risks that you reject, and we have a few examples in the paper. The second is what we call range compression. Edward Tufte, he focuses on graphical displays and how to present information to people. He calls this the lie factor in a different dimension. And basically, it's that the heat map really distorts the scale by quite a bit, right? Every consequence bigger than 20 million is in this bucket. So we'll talk about that in some more detail. And then the last piece is I'll demonstrate how just arbitrary decisions about the design of the heat map, when you're building the heat map or the risk matrix, arbitrary decisions that you make about its design can change the ranking of the risks. So here's an example with this range compression. Here we have a risk matrix that we heat map that we took from oil and gas industry. We've got probability here, moderate, 5 to 25%. There was some alternative here, A, or some risk, and it thought the impact level would be very high, greater than 10. That should be million in this case. Okay, and so let's say A had a 6% chance of occurring with an $11 million impact loss. That would be what I've shown over here. Okay, and that would put it in this cell. Let's say B had a 5% chance of occurring, so less than A, but it had potentially a $1 billion loss. That would put it here in this category because it's 1% and greater than 10 million. So B would be a yellow risk, and A would be a red risk. Color slightly different here. When I think most of us would agree that B is quite a bit more concerning. And if you multiplied these probabilities times the dollar amounts to get an expected loss, you'd get that the expected loss of B is much higher. But the risk matrix would suggest that you should focus on A. You could have risks that are within the same box but are grossly different. So we have a 6% chance of $11 million loss or a 24% chance of $1 billion loss. Both of those would be within this cell, but again, I think it's obvious that these are very different. And this is happening because we've compressed the scales by so much, and how we changed the scale was not consistent from bucket to bucket. So it's a gross distortion of kind of the underlying risks that we face. And so there's a view in really how to present information to people, and it's that when you're showing people information, you should avoid confounding design variation with data variation. Your design of your display shouldn't grossly distort what you're trying to show people. And heat maps really do this in non-uniform and uncontrolled ways. Tufte introduced this lie factor. He studied many graphics, not heat maps, but other types of graphics. He would define the gold standard as being 1-to-1, that we haven't distorted the information we're presenting to decision makers in any way. In what he studied, he found a lie factor of about 15 in the domain that he was studying, which he called a whopping lie factor. We looked at the SPE literature, and on average, we found a lie factor of 122 in heat maps. So it's just a gross distortion of the information that's being presented. So they're supposed to improve communication, but it's highly distorted in terms of what you're showing people. The next thing is this arbitrary ranking. And let's go back to this example that I showed before. At first, we counted up from 1 to 6 and 1 to 6. So higher numbers were worse, and we multiplied them. So for severe losses, we multiplied 4 times 5, and we got 20. And then we ranked them based on this risk score. And severe losses was ranked first and blowout lowest. Okay. Well, what if we counted down instead from 6 to 1? Okay, that's no reason to do that. I mean, if you count up, we could count down, and we could go with the smallest number. So something that has the smallest number is the biggest risk. Well, if you do that, you're going to get that severe losses is a 6, well controls an 8, and blowout now is a 5, has the smallest score. So simply by changing whether we count up or count down, we get a complete reversal of the rank order of these risks. And if we have scarce resources and we're trying to decide, well, which of these risks should we address, the completely arbitrary decision of counting up or counting down changes the decision that you make. Okay. And we looked in the SP literature that about 20% of the papers count down, about 80% count up. And my question just to ponder would be, what other best practice produces different recommendations simply by changing the scale? Right? Imagine a civil engineer, they design a bridge that needs to be safe and support traffic. If they design the bridge using meters, they get one design. If they design it using feet, they get a different design. Right? That'd be malpractice. I mean, something would be wrong there, yet risk matrices have that feature. So in my view, a tool that produces arbitrary recommendations can't be considered a best practice. They may appear authoritative, rigorous. You may believe they improve communication, but it's really the illusion of communication. It's distorting communication, and it's potentially altering the decision-making in arbitrary ways. These flaws are inherent in the design of risk matrices and can't be corrected. Anytime you're going to compress the scale that is like it's required in a risk matrix or a heat map, you're going to introduce problems like this. So instead of heat maps, we'd recommend the use of decision analysis principles of decision quality, which have been rigorously developed and tested really over the last 300 years. So given this, we have another poll here. We'd like to get your view on heat maps or risk matrices. Please make a choice. First is they're fundamentally flawed. We should use other methods. Second, they're flawed, but it's the best tool we have. Third, they're a useful tool that I think we should continue to use. Or four, they're an excellent tool and no changes are required. So if you'd make your choice there, and then we'll be able to share that with the group. And then we can go on to talk briefly about some alternatives to heat maps or risk matrices. The poll's wrapping up. And so, okay, happy to see only 1% think no changes are required. Half of you that these are flawed and we need to use other methods. Flawed, it's the best tool we have, and then useful tool we should continue to use about a third of you. Okay, so I encourage you to look at the paper that we put on. You can email me, or I think you could access it online, and you can see some more of the. There's other flaws that are built in besides the three that we covered here. Okay, so I think the perspective that I'd want to take is that risks are only managed through our decision making. Risk management is about making high quality decisions, and the science for how to do that has been developed over the last 3 centuries and is taught at many accredited universities in the US and overseas. In addition, the SPE recently published a technical report on how to make decisions in complex, uncertain environments. And that report is all centered around the use of decision analysis or decision quality. And so I think an important point is that decision making is a professional discipline. It's not something that anybody can do without training or with an hour of training. It's a discipline that requires education, training, and apprenticeship. So with that, I'll turn it back over to Lynn, and Lynn can tell you how to learn more.
All right, wonderful. Thank you, Eric, for bringing us your expert insights on heat maps, whether we should use them, whether we shouldn't, whether there's a better alternative. That was very interesting. As we prepare for Q&A, I wanted to just share with today's participants how they can take part in more in-depth and expanded programs if they're interested in doing so. Move on to our slide here with just upcoming courses for this fall. You'll see several classes that are coming up in September, October, and November. At the bottom, you'll see a little guide as to whether they're required or electives for our SDRM certificate if you're interested in that. And you'll also see information on the website and email if you want to contact us for more information. These classes will give you more insight and more in-depth understanding of the things that Dr. Bickle was talking about today. Two of the classes in particular, the Achieving Strategic Decision Quality and the Decision Analysis and Value of Information classes coming up in September and November. Particularly, we'll go into some of the things where Eric was talking about some alternatives to heat maps and what kind of processes that he was suggesting, and didn't have time to go into obviously in our quick webinar today, but wanted to give you that opportunity to join us in person for those classes coming up. And as we are getting ready to go now to Q&A, I just wanted to we are going to put up one more poll just to get a little bit of insight on your level of interest in the certificate program. If you would share that with us, we would greatly appreciate that. And then we will go back to Eric for a question that's coming in. Eric, we have a question about how to avoid biases in this decision-making process, and maybe using heat maps or not using heat maps creates more or less biases. Can you comment on that, please?
Sure. Thank you, Lynn. Yeah, in the interest of time, we didn't have time to dig into all the different approaches and the courses that are offered, but participants could look at the program. There's a real process for how to make complex decisions organizationally and uncertain decisions, it requires some study, and part of that is how do you make sure that you get good inputs, high quality inputs, and understanding the types of biases that we are susceptible to, and how to overcome those or at least mitigate those is an important aspect. And I would think that heat maps are as or more prone to problems with bias, even in terms of how people interpret color, than some of the other processes.
Awesome. And I did mention the biases class, I think was one of our September classes coming up. So we actually do spend 2.5 days on biases and decision making during that class. It is very much going in depth of the opportunities to make decisions that are based on biases as opposed to make decisions based on good facts, and how to avoid the biases. So I wanted to thank you again, Eric, today for sharing your time and energy with us, and also to our participants. We hope that you've enjoyed this today, and we are going to have time to answer some additional questions for you offline if we didn't get to your question online, but that is all the time we have for today. So we look forward to connecting with you again soon. Take care and have a wonderful day.